All right, this is last time, of course, we spent most of the time just tinkering with symbolic regression, right? You were playing around with those CSV files, which contain just data that I generated based on some functions, and then the game that we were playing was you try to find the function that I used to generate the data, right? You were doing symbolic regression. I gave you the data the function had, right? So right, we had something like this, right? Where I gave you the x values and the y value, but the question was, what is f, right? That's the game we were playing. Your job was to find f, right? You remember that from 2 days ago? Okay, great. For the sake of time, we're not going to do that one again, although I'm tempted to, solely because a core of the class isn't here, and I don't know if they'd miss it, but whatever. For this particular problem, in order to get anywhere, you would have had to tinker with the language, because there was a point where I started adding trig functions into what the functions were, but the language you had didn't include trig functions, so you'd have to like play around. Also, I talked a little bit before about with genetic programming that there's a bit of a feedback loop. If you keep seeing your GP system producing results that always had like x squared plus 1, you could add that to your language and then try running again. Meaning, like, if the search kept thinking that x squared plus 1 was really valuable, maybe add that as like a single function, a single part of the expression to your language. And then suddenly you kind of like help the search a little bit because it's seemingly important. What else? A lot of people were kind of observing that their functions were, like, first of all, it took a little while to run. Yeah, that's normal. And they noticed that their functions were like hilariously large. Well, that's a bit of bloat, right? We talked about bloat. That's a perfect example of it. And there were a couple of things you could do to control bloat, which was implemented in the example I already gave you, where you limit how big the trees can get. But the default limit I gave you was pretty big. So you could have lowered those bloat limits, or raised, however you want to think about it. You could have restricted the size of the trees more, and you probably would have had faster searches and more like succinct functions that it generated in the end. But, like saying, still do not expect, like, you should absolutely expect crazy looking functions that require some like simplification in order to make sense of what on earth they actually are. And oh yeah, one thing to note as well, by the way, if you were wondering, like, well, how come all those functions were, oh, okay, yeah, another problem was in the language that I gave you by default, it only enabled you to have integers as constants, but some of the functions I generated used floats. Now, there would be ways for your GP system to get floats. For example, you could have like, like even if your GP language didn't include floats as constants, your GP system could try to like figure it out by doing something like I'm thinking of like 1.1, right? It could do like 11 divided by 10, right? Like, so it can still create floats, but it's got to go out of its way to do so. And I believe I restricted the language to be, in the language, I believe I restricted the constants to be between like, maybe like -10 and +10. So how could you get 11? Easy, 10 plus 1 divided by 10, right? Like the GP system can keep trying whatever it wants to do to fit the data well. But then again, it might be easier to just include floats. But as soon as you start to include floats, like the functions I gave you, like imagine you started including floats as constants, okay? Again, not impossible, but if you started including floats as constants, But the function I gave you, let's say it was like f of x equals x plus 1, right? Well, if you're including floats, what are the odds? Who can tell me the right answer? What are the odds of getting exactly 1 as a constant if you're using floats? Like close to like 0, right? It's not going to happen. It could happen by doing something like x divided by x, right? It still could do stuff like that, but, you know, just be aware of how all of these ideas, the language will affect what you got. Am I recording? Yes. What else? The data points. And yeah, if you saw, like I generated a function that looked like this, like I think the first function, d0, was like this, right? But why on earth did you, like when you open up the CSV file, why was it just full of a bunch of floats, right? If this is the function, like what's going on? Well, first of all, whatever these were may not have been integers, but I also had like, I added normally distributed noise to each of it, to each part of this, meaning you're going to get error, okay? Like I specifically added noise to the data to like make it more tricky, but if the noise is normally distributed, let me make sure this is clear. Let's say I've got a plot like this, and the data points are perfectly like x squared, right? And you want to fit it, it's going to look something like this, right? It's going to fit it perfectly, let's say. That line's going to go right through each data point. But I added noise, okay? So really, if the data was like, well, here's the x, here's the y, I went up and I actually I changed it a little bit. So it wasn't there, but maybe it was like here. And this one was like here, and maybe here, 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 right? So the x's are like where, the dots are where they should have been, but because I added noise, they looked like this. But, and keep in mind too, like how many data points were in each of those files? A lot more than 1, 2, 3, 4, 5, 6, 7, 8, right? There were a lot more than that. There were a lot, right? So you'd have stuff like this. So that's why you're not likely to get something that's why your functions are going to look a little crazy, right? And maybe like your mean squared error is not going to be 0. And because it's not 0, you'll never get like the function exactly. But often you would look at it and be like, it's really close to like, let's say you got like x plus 1.0274, right? You'd look at this and be like, maybe it's x plus 1. You know, you might want to like really simplify it. Maybe if you make it x plus 1, the mean squared error might even go up. But what's nicer, this or this? You know, so there's always a bit of a trade-off, right? Right? So the noise, we concede that the noise exists, meaning, well, should I really be expecting something to look like? Maybe, right? But, you know, do you see my point? No? Because the data is noisy, you're not really going to expect to get like something as clean as this in terms of your actual function you generate. Okay? I know in your example you probably did, but let's say, for example, yeah, it's not going to look something like this. Maybe you get something that looks like this, right? Because maybe this actually fit the data better after the noise was added. Do you see my point now? Right? This might be the real function, but there was noise, and maybe this fits the data with the noise better than this. Okay? That's my point. But it's because of noise. So because we know there's noise, like, you know, if someone hired me to find the function and I was like, well, this, would I be better off giving them this or this? You know, I don't know. We can only really tell by maybe if we had more data and we can compare like testing, training, testing, you know, something like that. Yeah, do you see? Now, assuming, and this is a reasonable assumption most of the time, by the way, assuming, why did I add random noise? Well, if you were to go out into nature and start observing things, you're never going to get anything perfect. You're going to get things where there's always some noise, some measurement error, not everything's perfect, my ability to record information, noise is going to happen. But it's entirely reasonable to expect that the noise that you see is normally distributed. What do I mean? I mean 0. It's going to look something like that, right? Most of the errors that you're going to get are going to be really small, right? And for every error over here, you're equally likely to get an error over here. And same with over here, and same with over here, right? So, because the errors will be like all over the place, and if you have a sufficiently large amount of data, you could actually still expect your GP system to kind of cut down the middle, which is pretty great, actually. Do you see what I'm saying? If the errors are normally distributed on both sides, this is going to be the line, like the line of best fit is going to be between them, right? Right? So, yeah, there's noise, but actually GP is kind of robust against normally distributed noise. In the same way that regular linear regression is as well. Now, if the noise we have is not normally distributed, okay, we might have some trouble, but usually, often it is. Any questions about any of that right now? All right. I did a little bit before talk about multi-objective problems. Sometimes you've got a problem where there's two things we want to optimize. We want to optimize, for example, one of the classic fun examples is like factory output while minimizing worker death, right? So we want to optimize two things. Maybe I can get more output of my factory, but more of my workers die. People don't like that when that happens. So we have to kind of like balance these things. So at what level of worker death am I okay with is basically what we're trying to figure out here. This is a fun example that people used to use, right? So obviously it's morbid. So sometimes we have a situation where both objectives complement each other, okay? Sometimes you have objectives that are in direct conflict with one another. Factory output, I can maximize that, but the likelihood of people dying on the job goes up, you know? Or I want to buy the biggest house for the smallest cost, right? If I go bigger, price usually goes up, but I want to minimize price. So sometimes these things are in conflict with one another. There are a lot of ways to deal with multi-objective problems. Some easier than others, some better than others, better. But at the end of the day, multi-objective problems are a thing. How many objectives are there? There could be as many as you want. If you start to have too many objectives, it's going to be really difficult for your search to do anything. But having something like 2 objectives is entirely reasonable. When you were doing, there was only one person in here who was not here today who did that vehicle routing problem. That was a multi-objective problem. You want to minimize the total distance while also minimizing the total like vehicles used or something like that. I can't quite remember. That was a multi-objective problem. What we could do with genetic programming is we could, because often bloat is a problem, we can bake into the system. So we've got like a very explicit restriction on the size of the trees. The bloat control things. Don't let them get deeper. Don't let them have more than so many nodes. There's those explicit like caps. But we can bake in bloat control into the evolutionary search by making the size of the tree part of the fitness, right? There's an idea. What if we had two objectives? Fit the data the best while also being as small and succinct as possible. Succinct just means like brief, like to the point, right? So x plus 1 is very succinct. X times 2 divided by x plus 2 over 4 times 2 is not very succinct, right? So you could actually add selection pressure to prefer smaller trees. If you have a tree A and a tree B that both have very similar fitness values, okay? Let's say they're very, very, very similar, meaning that they're probably very similar in terms of what they mean semantically, let's say. But if this one is smaller than this one, prefer this one. Now, how do you kind of deal with multi-objective problems? Well, there's a whole topic on that that's coming up soonish. But one of the a little spoiler, one of the simplest ways to do it is a weighted sum. All right? Where basically, and that's what Deep wants to do. Deep is like ready for a weighted sum really easily. A weighted sum, you should all be really familiar with. Will be like, okay, my fitness equals weight 1, objective 1, plus weight 2, objective 2. Let's say. Where this could be like, okay, how well does, like, what is the mean squared error, right? And this is, how big is the tree, right? Now I want to minimize, so we'll have to tinker with that. But if I had a mean squared error of like 70, a mean squared error of like 2, and this over here had a, the weight here would be like -1, so you actually would just like subtract, right? Usually you would have the weight -1 times, and let's say your tree has like 17 nodes or something, right? So based on that, like, okay, 2 minus 17, like, which, I haven't decided what weight 1 is yet. That's kind of the problem we have, right? Right now, though, if you're looking at just the raw numbers, mean squared error, you want it to be like really, really small. And you want this to be small too, right? But the size of the trees are on a wildly different scale than what mean squared error is. Meaning, if I were to just like add these together, the size of the tree is going to absolutely dominate the, like, what we're selecting for, right? Because if I have one over here, where this one has a mean squared error of like 7, but it's got a plus -1 of like 15, right? We would be like, oh, well, let's make it something like 11, yeah. Like, oh, well, okay, this would be, oh, pick this one, the 11, that's way better, right? But I don't know, I feel like we should probably be prioritizing the mean squared error more. Do you see my point? Right? Also, the weight -1, that's not right. I'd have to make it like plus. We want to minimize. They're both minimizing. So the weight would be still positive. Like it cancels each other out. Yeah, that's fine. the weights, they could be the same cardinality, or same direction. Now, so weight 2, whatever. So this turns into a game of, well, what should the weights be? If I really want to emphasize this being more important, I can make W1 bigger than W2, for example. And I would adjust it accordingly such that, like, well, really, what do I want to do here? I would say, like, okay, if all things being reasonably equal, pick the smaller tree. That's how I want to make my decision, right? I don't want to be like, that's a smaller tree, pick it. Well, was its mean squared error way worse? I'd rather have something that fits the data better and is big than something that's small and doesn't fit the data at all. So when you're dealing with multi-objective and you're doing a weighted sum, you got to think about what are the weights going to be. And by the way, in deep, one sec. In deep, if you remember how like the fitness function returned a tuple, right? And that would be the objectives, the values of each individual objective. And if you remember when you're defining the language and you're setting up your GP system, you need to give it like a weights, which was like a weird tuple, right? That tuple would be, well, what are the corresponding weights for each one? Okay? By the way, you had a question.
Would it be helpful to like normalize the tree?
Absolutely, yeah, you could, wait, hold on. Finish your question.
Like just to scale it on a similar scale as the...
Well, that's effectively a weight though, right? If you normalize it, it's effectively a weight. Now, you could say like, well, what if we do like a dynamic weighting where it's like on the fly z-scar or something. Yeah, there's like a lot you could do, but ultimately at the end of the day, it's kind of like the same idea, right? What gets tricky though is if you only focus on this value and you kind of ignore what's going on over there, you don't really know, like, well, like I can't like backwards engineer it if I don't remember what came where. So it's often important, like, do keep track of what the hell's going on here. You're going to want to know that information. Yeah, here, when you're creating it, a fitness min, weights. Here's one where it's two objectives, both we want to minimize. Great. And here, because it's 1 and 1, that means that they're comparatively, like the weights are the same. I don't really pick one over the other, right? What is this problem for? This is for this is just general purpose. It's not even for a particular problem. So in what problem would it make sense to have two things being equal? I don't know. It doesn't really matter to me. But the point here is the number of values you have in here would correspond to the weights for each of the objectives. And if your fitness function, if this has like 6 values in it, your fitness function better return its tuple of size 6. Yeah, have a fitness function return multiple values. Like here you go, yeah. A and 1 divided by B, sure. Cool. Any questions about any of that? That was just some like deep tips and tricks. All right. Tuning hyperparameters. This is a lot of what you're doing when you're using a GA and whatnot, right? At least it's a lot of what you're doing initially. Because like if you're using evolutionary computation, you pick your algorithm, you set all your like symbolic hyperparameters. Those are like what mutation you're going to use. How are you going to encode it? What's your selection, right? And you set all the respective numerical hyperparameters. I want a crossover rate of this. I want that many generations, population size of whatever. You got to play around with those values. Don't be the fool that sits down, puts in some values, hit runs, and be like, there we go. That's never going to work. You got to like tinker a little bit, right? And there's a lot of, there's like a correct way to tinker, right? Who here remember, like who here is taking like machine learning or data science? One person, 2 people? In the past, yeah, you don't have to have it now. So you remember like, oh, you're training, validation, testing, you know, that's how we can decide. Yeah, like that's important as well, right? But often when you get started, you could really just like follow your gut. you gotta have enough experience to be able to follow your gut. Like, you don't even really need that much of rigor to start getting your hyperparameters set. And then if you really want to make an argument that I found the best hyperparameters for this particular problem, which is usually not an argument people want to make, because people are like, great, just screw around with the hyperparameters until it works, right? You're just like following your gut and getting a sense, okay, yeah, this seems to be working really well. That's often what people are doing. But tuning your hyperparameters is important. You got to have a sense of like, how do you navigate the space of hyperparameters? And that's what today's topic is, just to make sure you kind of understand it. Because a lot of this is like, what's your gut say? Yeah. How do you put that in a report? Usually what you see, this is what you see in published articles. Hyperparameters were determined empirically, which is a fancy way of saying you just screwed around until you're like, that seems good, right? Because often, like, if I'm reading an article where someone's like, wow, we came up with an amazing solution to this crazy complex problem by using a GA, right? It's not really common for people to be like, if you came up with a really good solution and you used a GA, if there's someone in the room that's like, well, what was your crossover rate? Could you have a better one? If someone's saying that, people are going to be like, go away. Like, that's not what this is about. It's about finding the solution, right? So when you see like, oh, these values were determined empirically, that's usually that's usually what you see. So I know you thought you were like, well, how do you say that? That's how you say it. There is an answer to that question. Yeah. So that's like the first part of the GA. And then there's the end of like, okay, interpreting results. And maybe those results tell you how you can go and tune those hyperparameters more. Or maybe that's enough and then you can carry on with your analysis and figuring out how you like, okay, so what does this mean in the context of what we're doing, right? So evolutionary algorithms also are criticized for the number of tunable parameters. And that's a very fair enough solution. Some people say like, well, that gives you the flexibility. And some people say like, I'm just wasting my time screwing around with all these values. But then again, most people are still also not going and fine-tuning these knobs too crazily. They're often just kind of like, this seems to be working really well. I'm sufficiently happy. Let's go. Does there exist a better set? Almost certainly. If you're dealing with real numbers, you're not going to find the best one. It's impossible. So, yeah. All right. So all evolutionary computational algorithms require some hyperparameter tuning. That's great. If you sit down and hit run once, you're doing it wrong. Given the modular nature of the algorithm, there's a lot that you can do. Each part of the algorithm itself is effectively a hyperparameter, which may or may not come with additional knobs to turn, right? When I say knob, I mean like think of like an old radio where you're dialing it in, right? Not even like new radios are like that too, right? You know, a dial. Everyone's looking at me with a blank face. Do you really not know what I mean when I say knob? You're not helping me. Oh my gosh. All right, fine. Think of a circle that you can spin, okay? Like a dryer. Who here used a dryer before? And you set the timer? There, that's the knob. There you go, all right? Now, why a knob? Well, often you've got like, you know, some knobs that go like click, 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 click. Well, that would be like integers, right? You know, click very discrete values, but some are like continuous, right? So that's why I use the word knob as an analogy for tuning those hyperparameters. Okay? Okay. What's the best way of finding it? There isn't one. There isn't. Mostly because at the end of the day, technically, you ain't going to find it anyways. It's going to be impossible. So symbolic versus numeric hyperparameters, we talked about this before. What are the symbolic hyperparameters? Those are things like what's your crossover? What's your selection? Okay? And then the numerical hyperparameters are going to be like, well, what's the crossover rate? What's the tournament size? Right? Okay. So here, this would be like crossover rate. Really, that's like a continuous value. Although usually people aren't going to type in like, oh, I got a crossover of 87.721444, right? It's that would, if I saw that in a paper, I'd be like, what the hell? Like, there's like, no, stop it. And then tournament size, well, that's going to be like an integer. Regardless of the hyperparameter type, we need to set these things, though. And we need to set them based on something. At this stage, you're new at this, so you're going to sit there and be like, well, why would I want tournament over roulette wheel? Why would I want 1-point crossover or 2-point crossover, right? Like, why? When you're new at this, you're not going to have an answer. Even if you're really experienced, you might not even really have an answer, but you've got a bit of an intuition, and someone says why, you go like, I don't know, I just got a feeling, right? You just try things. And if it works, good. If it doesn't, you think you can get better, yeah, try 2-point crossover or something, right? Why might I pick 1-point crossover? I might say like, well, based on like what I'm doing, I really want to make sure that my variation operators, the genetic operators, aren't too destructive, right? So I'm going to pick something where like 1-point crossover is really not too destructive, right? Or maybe I want a uniform crossover. That's very destructive, right? Maybe based on what no, that's what I want, right? So there is some information I can use about the problem that I'm doing to help me make informed decisions about some of these things. But at the end of the day, remember, we're using these things for sufficiently hard problems where we don't really know what else to do, so we're just trying whatever we can to see what sticks. That's why we're using this computational intelligence. So we need to make decisions. Symbolic hyperparameters may introduce additional numerical ones, right? Like roulette wheel often doesn't, it can depending on if you want to like modify the results from roulette wheel, but like your base roulette wheel, there's no additional hyperparameter, right? You do roulette wheel. But if you're doing tournament selection, well, what's the tournament size? See, that's what I mean. Some have more than others. Typically, symbolic hyperparameters are more high level, and numerical operators are more low level, okay? In an evolutionary computation instance, and by the way, I'm going to use like precise wording here that you don't really see very often, but this is technically true. An evolutionary computation algorithm instance is one where you've set everything, okay? The algorithm setup is like, what am I going to do? Okay, like GA, and I've got everything. But an instance is one where like, okay, I've got everything set and I'm about to hit run, okay? So how do we tune hyperparameters? There's no silver bullet strategy, okay? Often some reasonable starting values are picked where you use your intuition to the best of your ability. The more experience you have, the better your intuition becomes, just like with anything. But then you just kind of go from there. So there's no correct starting values, although there are, let's say, better ones than others. Yeah, you get experience with what's typical. Additionally, what one may argue is typical will differ between evolutionary computation algorithms and even problems instances, right? So like for a GA, a crossover of 80, mutation rate of 20, entirely a reasonable starting place, okay? But for GP, a mutation rate of 20 would be shockingly high. You'd probably want something lower. But that really depends, right? There was one time I was at a conference and I had a very specialized form of genetic programming that I created. And because of like how it was done, a higher crossover or a higher mutation rate was very valuable to me. It gave me the best results. And I remember people they just like argued with me about like, no, it should be like 5% tops. That's even high. What do you 20%? What do you do? It depends. It depends. It depends. It depends. It depends on the encoding. It depends on what the population. It depends on a lot of different things. I'll get rid of this just in case. Yeah, some symbolic hyperparameters have, oh, I already said that. For example, tournament, yeah, great. For population size, so okay, we set mutation, we set crossover rates. So what about a population size? What about the number of generations? I don't know. Pick a reasonable number, maybe a population size of 1,000, and try 1,000 generations. Plot what you get. What did that learning curve look like? Did it look like it was still learning? If it was, crank up the generations. Does it look like it's converged? Okay, try upping the population size. Does it continue to learn, right? So this is one where there's more of a feedback loop. There's still a big feedback loop for the others, like what's your crossover and what's your mutation, don't get me wrong. But I find like the number of generations and population size are a little easier to kind of like pick because of how like obvious it is. Let me be clear. If you hit run and then it stops here, right? I would say, okay, and this is like generations. You look at this, I would say, run it for more generations. It's not done. It hasn't converged, right? So there, very easy, crank it up, okay? Maybe next time you hit run, it looks like this. Okay, cool, perfect, 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 perfect. Ignore the y-axis in terms of height, right? It looks like it's converged. Okay, cool. I could probably even cut back on the number of generations, but you know what? Let's crank up the population size. Maybe that'll help. And maybe I crank up the population size and then it starts to look like this again. Okay, well, I can crank up the number of generations. If at any point when you're doing this and you're saying to yourself, man, these algorithms are going to take a while to run, yeah. But if you can make it run longer and get better results, that's the point, right? So don't be afraid to just keep cranking it if it still doesn't converge. That's what you want. And like, look, during my, like some of the work I've done, I had population sizes of like 10,000 and generations of like 10 million, right? This is the way it is sometimes, right? Yeah, okay, some hyperparameters may need to be adjusted as other hyperparameters are changed. In hypermarkets, that should be hyperparameters. I don't even know how that happened. Is hypermarket a word that like autocorrect did for me? Oh, so this basically means we've got a complex system. We have a nonlinear, dynamic, chaotic, complex system, okay? What's that mean? It means that, turns out, like you ever play one of those games where, think of like the old video game, right? I feel like I remember asking the students this last year. No one had any idea what I was talking about, but I'm going to try again. Let's say you have a grid like this. Right? Okay. And these are like little buttons that you can press. They're either going to be blue or red. And your job is to make them all red. Right? Maybe this one's like blue, this one's blue, this one's blue, and this one's blue. Right? Right? And then your job is to make them all red. So you're like, okay, well, I want this one to be blue, so I'm going to touch it. But when you touch it, this one flips, and this one flips. You know those little games? How does no one know what I mean? You know what I mean. Maybe it's a generational thing. I don't know. But there's like, I don't know, it's like a game. The point is, and you're like, oh, shit, okay, well, I'll press this one. Great, and then that one, okay, well that one flips, that one flips, that one flips. But then this one flips and this one flips. And you're like, okay, and I'll press that one again. Okay, well that one flips, that one flips, that one flips, that one flips. And you're like, okay, look at that. Okay, well then I can click this one. That flips, that flips, that flips, that flips. And so on and so on and so on. You see? Okay, you have no idea what I'm talking about. All right, fine. The point is, every time you change one thing, like, let's say you're like, okay, I found the best crossover rate. Perfect. Now I'm going to go on to mutation rate. And you change mutation rate, suddenly your crossover rate that you picked was shit. You need to actually go back and change that. All of these values are so inextricably interconnected that you've got this like crazy spaghetti, and none of these things are independent from one another. You know the game Pickup Sticks? Gosh, I'm so... Right? And you're like, okay, go pick up that yellow one right there. Oh, yeah, okay, that's not what I want. But like pick up that yellow one, right? You have to pick up that one. Or maybe you got to pick up this one. You're like, well, I can't, because if I pick that up, I screw up all those things. You know, it's chaotic. It's complicated. All right, it's reasonable. Okay, yeah. Yeah, okay, it's reasonable to increase the population. So, like, here's an example, right? Population size and tournament size. If your population gets so big, you might need to increase your tournament size, right? So, you know, some of these things, they affect each other. That's the big point. Any questions so far? All right, so empirically thinking, once the hyperparameters are set, initially the algorithm should be run an instance. You hit run to get a sense of performance, all right? And based on the performance, the hyperparameter values should be tuned, right? This is the feedback loop. This is that loop of tuning, okay? So sometimes when you change a hyperparameter, it has a big impact on the performance, okay? That sometimes happens. Sometimes you've got a hyperparameter where when you change it, it has no real impact on the performance. However, it gets crazy because maybe once you pick this, the shape of this changes, right? So the point I'm making here is once you find one that's good here, what value is good here is going to change a lot. Yeah, so yeah, they're complex interactions, right? So parameter value, problem, and performance. Yeah, so problem, parameter value, yeah, okay. Yeah, all right, so it's complicated, right? And this is going to depend on instance to instance, problem to problem, like problem instance, like think of TSP instance to TSP instance to TSP instance. What parameter values work best? That can depend on each instance, right? Depending on the problem you're solving, it's going to depend. There's never going to be like a static set of parameters that you're going to pick and be like, this is what you do whenever you're using a GA. It's never going to happen. It always depends on so much stuff. And what do you expect? Because, again, we're only using something like genetic programming, genetic evolutionary computation, computational intelligence. We're only going to use these big, beefy algorithms when we've got no other choice. And we don't want to use these algorithms. They're complicated. They're hard to deal with. They're hard to interpret the results, right? We don't want to have to use them, but sometimes we just do. So expect it to be a pain in the ass to get things set up in the first place. That's the name of the game here, right? If we could use something like k nearest neighbors, where all you have to do is what's k, do it. If you can get away with using that algorithm for your problem, do it, right? But we're not looking at problems where something like k nearest neighbors is going to work. We're looking at problems where it's like, I don't know what else to try. So we whip out the big guns, and the big guns require a lot of like muscling to work. Make sense? Makes sense. This is not a downside of evolutionary computation. This is a downside of the nature of the problems we're solving and the type of algorithms we use for those problems. Okay? Yeah. So it's foolish to search for the best hyperparameters. Don't get stuck, because you could spend days tuning hyperparameters, especially when you hit run and your run takes 4 hours, right? You could start to take a long time tuning hyperparameters. Yes, do your tuning. Take your time, figure out what works, okay? But at the end of the day, don't go crazy, because you're not going to find the best. Spend some time, pick something that seems to work reasonably well, and say like, we determined it empirically, and people are going to go like, yeah, okay, cool, got it. The trick is to run the algorithm, repeatedly tune it. With experience, this process gets easier. There does exist algorithms that will do like an automated like grid search and strategy of like tuning hyperparameters. There do exist algorithms for that, but they don't tend to be overly popular. They work, but it's almost like overkill, because everyone's like, you just play around until you find something good, right? Something like these algorithms, though, that find the best hyperparameters are going to give you things like crossover rate of 82.721442, right? Like, what is that, right? Like, just 82, fine. Even 82 is kind of crazy, right? Feel free to try them out. You could pip install, my favorite thing, right? Like, you absolutely give it a go. It's worth a shot. Some people, there's like, you could do like metagenetic algorithm where, like, okay, you also make a GA to evolve the parameters, right? Which is kind of crazy. But then that begs the question, well, how do you determine the parameters for the GA to find the parameters for your problem, right? And then you could just play that game forever, which is kind of silly. But one way to kind of address that is like, well, what if you kind of like tack on to the end of your chromosome? Let's say you're doing like TSP, right? And somehow you like smush on a chunk at the end of the chromosome where you've got like crossover rate, mutation rate, whatever, 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 and those values can change throughout evolution as well. So you could actually make it kind of like manipulate itself, which is kind of neat. Give it a go, see if it works. Good for you. Any questions about any of that? Yes?
When you're talking about different instances of the algorithm, like, is there a way to note, like, what parameters you're using? Like, you should use, like, declare that somewhere and then just use short form, like, variable later in the paper? Or...
So in the paper, often what you'll see are like maybe tables to be like, here's what I have. This is what I landed on, right? And usually, like, again, you can say like empirically, if there's anything in there that might seem peculiar, which you probably wouldn't at your level, and this is not to like dismiss your abilities, it's just you don't have a lot of experience with evolution computation, so you won't be able to maybe recognize what's peculiar. But often if you're reading like a journal article or something where like you're using genetic programming and you've got a mutation rate of like 30%, like that would be very unusual in general. So you would then explain like the unusualness, well, getting tongue-tied. You would explain what is unusual, but most people, like, if you've got your algorithm set and you've got all of your parameters are kind of in like, yeah, those are like normal, what you expect to see, and you say, these values were determined empirically, people are going to go like, yeah, okay, cool, that makes sense, right? Yeah. Does that answer your question? Sometimes I've seen, like, I like it as a table because it's just boom, right there. Sometimes I've even seen it just written out in paragraphs, fine, whatever works. All right, and the next topic is what comparing distribution even means. And that's what we'll talk about on Monday. All right, have a great weekend, everybody. Enjoy assignment 2.